All right, so here is section 2.2, and we're going to talk about the chemistry of water. Water is extremely important when we are talking about life. All living things, all chemical reactions that help living things to live need to happen in water. The first life that ever evolved on the planet billions and billions of years ago had to happen in water, and for a long time that's the only place that it existed. It is so important that it's the first thing, really, that scientists look for on other planets when we think that those planets could have life. If they don't have water, then they really cannot support life. So water is really important to all living things. And the first way that it's really important is because you are, or your cells really are, full of solutions. So let's talk about what a solution is. When you talk about a solution, it's not just one thing, but it is a mixture of things. But the mixture is even. So solutions are mixtures in which one or more substances are uniformly distributed in another substance. And what uniformly means is it means evenly. You might hear the word homogeneous. E-N-O-U-S, homogeneous. So all of the parts are spread out really equally throughout the whole thing. And it's made up of two big parts, two major components. And that is the solute. So this is what is dissolved. So this is the solid that you add into a liquid that eventually goes away, and that doesn't really go away. We at some point lose the ability to see it because it has interacted with what we call the solvent, which is the liquid doing the dissolving. So we have solute and solvent. For our purposes, the solvent in biology is always going to be water. So when you hear the word solvent, you need to think water. So let's look at this wonderful glass of lemonade. So the solvent is the water. The solute, the thing that has done the dissolving, is maybe sugar, because we add sugar to our lemonade. And maybe it's powdered lemonade. Let's say we went the easy route, we didn't make it ourselves. And it's maybe the powdered mix. So when we drink that, it's all evenly distributed. All that sugar and all that powdered mix are evenly spread throughout. So you don't get like big, or hopefully not, if it's mixed well, you don't get big chunks of like powder in your mouth or really strong sections. The flavor should be even. So that is the solution. And solutions come in different strengths. You know this. If you have made a glass of lemonade that's too weak, that means it has too much water. Or if you have a glass of lemonade that's too strong, then you need to add water to dilute it. So what that is referring to is the concentration. So that's basically how strong a solution is. And the real definition is right here. It's the relative amount of solute dissolved in a solution. So the more solute, look at here. So we have the more solute, the stronger the solution is going to be. Less solute means it has more water. The weaker the solution is going to be. So we can change this concentration by either adding more solute, and that will help the solution become stronger. It'll help it kind of go this way. Or by adding more solvent or water, we water down the solution. We make it more dilute. Another thing that we need to talk about when it comes to water is liquids have a certain measurement that we can refer to, and that measurement is called pH. And what pH stands for, it's what it's measuring. And what it's measuring is the concentration of H plus or hydrogen ions in a solution. Okay. So let's zoom back out and let's take a little look at it. So the pH scale has a couple of sections. So it goes from 0. Generally, we don't go down below 0, but it goes from 0 to 14. And in the center right here is 7. So this is neutral. So 0 and 14. Anything from 0 to 6.9 is an acid. And that means it has lots of hydrogen ions. Tons and tons and tons of them. Conversely, anything from right above 7 to 14 is not an acid, but it's a base. And that means it has really low amount of hydrogen ions. That doesn't mean that it's any safer. So generally when we think of acids, we think dangerous. So if we think something like up here, at the very top, battery acid, that's dangerous. You wouldn't want to get that on your skin. And the same thing is true down here, all the way at the bottom at 14 with lye. So lye is a component of soap, and soap is not harmful, but it's a component that we use to make soap. And if you get it on your skin, it's equally as bad as battery acid. So the further you get toward each end of the scale, so the further you get away from 7 in either direction, doesn't matter which way you go, the stronger that these substances are going to be. So up here, it's very strong. It's a strong acid. And down here, it's a strong base because we are further away from 7. So again, this is just a measure of how many H plus ions that exist in the solution. And here's another way to look at the pH scale. So again, we have 7 in the middle right here, and we have 0 and 14. Now I know I mentioned that pH is a measure of the H plus ions, so this guy right here. But there's something else. So if you are an acid, so anything from right below 7 all the way to 0, so this guy. If you're an acid, it means you have a lot of H plus ions. And the closer you get to 0, the more you have. And if you have a lot of H plus ions, then you don't have a lot of another kind of ion called a hydroxide ion, which is, if you couldn't guess, this OH. On the other hand, if you have a pH of above 7, so anything from right above 7 to 14, you don't have a lot of H plus ions. But you do have a lot of hydroxide ions. And what do you think would happen? What if we put an acid and a base together? Something that has a lot of H plus ions and something that has a lot of OH negative ions. So I want you to think about that for a second. Think about that H plus and that OH. And if we combined them, what actually would we be making? So if you think about it, we have H plus OH minus. And remember our little chemical equation. So these are the reactants. And then what's going to happen? H plus and OH minus is going to yield a product of H2O, water. So when we combine an acid and a base together, they react to make water, which is toward the middle of that pH scale. So when you bring an acid and a base together, the whole idea is to neutralize or bring the measurement of pH closer back to 7. And again, so if this is after the reaction, after the reactants, after the arrow, this is going to be not the reactants, but the product. And remember, sometimes you're going to have more than one. So again, you add an acid and a base together, H and OH negative. You're going to get H2O. So we're going to bring that pH back closer to 7. So this is just a reiteration of what I said before. So important things to remember about acids. They have a pH of less than 7. So that's what that means. Less than 7. It has lots and lots of H plus ions, which means it doesn't have a lot of OH ions. An example is the acid in your stomach. So you have lots of acid in your stomach that help you start to break down your food after you eat. And milk, if you look on your pH scale, guys, milk right here is slightly, very, very, very slightly acidic. Doesn't hurt you, not by far, but it's very slightly acidic if you were to measure the concentration. And then on the other side, so we then are talking about bases. So base is anything of a pH higher than 7. So higher than 7. And bases don't have a lot of hydrogen ions, but they do have lots and lots and lots of OH negative ions. So your blood is a little bit basic. And then ammonia, which is for cleaning, is a little bit basic. So neutral pH is water. And what that means is, I'm going to zoom in a little bit. What that means is that the amount of H plus is just about equal to the amount of OH negative. In reality, guys, remember, that's water. So I have equal amounts of H plus and OH negative. So that's why water, pure water, is actually neutral. It does not have a difference in the amount of the ions it possesses. So now it's really important to talk about the structure of water. So how water is built. And hopefully we remember how water is made. So water is H2O. H2O, which means that it chemically, we have an oxygen that is bonded to 2 hydrogens. And every single time we make a water molecule, it's always 1 oxygen bonded to 2 little hydrogens. Always, 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 every time. If we change that, we change the molecule. And they're held together by covalent bonds. So what that's telling you is these bonds right here, this bond and this bond between the atoms, they're covalent. And if we remember from talking about atoms and bondings in the notes for 2.1, when you're covalent, it means you share electrons. So they spend some time with oxygen and they spend some time with hydrogen. And the reason that atoms do this is because they want to become more stable. So hydrogens, each of these little hydrogens need this guy right here and this guy right here. They each need 1 more electron to be happy, to make them have a total of 2. And the oxygen needs 2 more electrons. So that's why it needs to bond with 2 different hydrogens, because it needs a total of 8 and it only has 6 in that valence shell. But this is so, so, so important. This idea right here. Electrons are not shared equally. So oxygen is a bully. Oxygen is bigger than hydrogen. So if you think of a tug of war, oxygen is like the really big, strong guy, and hydrogen is just, he's smaller, he's a little guy, and oxygen is going to be able to pull harder on those electrons. And the reason that that is the case is oxygen in its nucleus has 8 protons, which, remember, are a positive charge. And electrons have a negative charge. So positive and negative attract. So oxygen literally has more of a magnetic pull on those electrons. And poor little hydrogen only has 1 proton, 1 positive charge. So it can't pull on those electrons as hard as oxygen can. So oxygen is a big, big, big electron hog. It can't steal the electrons away from hydrogen, but it hogs the time with it. And a picture we should reference is down here. So let's look at this really quick. So this picture right here is normally how we represent the bonds that exist in a water molecule. So again, this is a covalent bond. But we're going to call it a polar covalent bond, because in all reality, if we look at this picture right here, this picture is more accurate. So oxygen is pulling those electrons toward itself. And remember, oxygen is bigger, so it can do this. And electrons have a negative charge. So think of it like there's like a cloud around here, right? And it has more negative now. And so that's why oxygen becomes partially, that's what this kind of weird little sign is. It means partial negative. And because all that's left in our little hydrogens, all that's left is the proton in the nucleus, we have an area of positive charge. So partial positive. Again, that's what these little guys mean. So that's really important. The fact that this happens is so incredibly important, because if this didn't occur, all of the properties that water has, that we're going to talk about, that make life possible, would not be able to exist. So this means, and the last thing I'm going to say about this slide, because water can do this, water is what we call a polar molecule. So polar, Polar, meaning it has areas of positive and negative on the same molecule. That's what being polar means. So our little oxygen up here, our little oxygen, or big oxygen I should say, is negative, and the little hydrogens become positive. And that's going to give rise to a bunch of behaviors that we are going to talk about. So this is just kind of in text what I just said. So water is a polar molecule, meaning it has areas of positive charge, our little hydrogens, and areas of negative charge, which is that oxygen, because oxygen is hogging those electrons. And this is all due to the fact that we have unequal sharing of electrons in the covalent bonds. And oxygen is hogging those electrons. So it's pulling them, again, like tug of war, it's pulling them more toward itself. And again, here's just another picture. Remember, these bonds right here are covalent bonds. So each of these represents electrons. These are the electrons that are being pulled this way. And same picture. So again, remember, this right here, that means partial negative. And these right here it means partial positive. So it's not a full charge, but it's enough to make a difference. So what's the point? Why do we even talk about this? Because you never have just one little water molecule by itself, right? So here is water molecule number 1. Let's talk about this. So this guy's number 1. This guy down here is number 2. This guy's number 3. So even in a drop of water, we're going to have millions and millions of water molecules. And they act like little magnets. So the positive area right here, this little hydrogen, when it comes close to a negative on a different molecule, this attraction right here gets really strong, or it gets stronger. Not super strong. It's actually a very weak connection, but it helps hold the molecules together very briefly. This is called a hydrogen bond. And they happen very briefly because, again, there are millions of water molecules interacting. So as they encounter each other, they kind of meet very briefly and then let go, and meet very briefly and let go. But when you think of this, I want you to think magnets. Positive is attracted to negative. If you put two positives together, like if a hydrogen came close to another hydrogen, so if we look, right, I'm going to put it in a new color. If we look right here, if these guys came too close together, what they would actually do is they would repel away. So they would shoot in opposite directions because they don't like each other, because the charges are the same. Same as if we put two negatives together, they would repel. So positive and negative are the only things that are attracting here. And again, here's just exactly what I said in words. So some things to be very careful of when you're writing this down. This is a bond between two different water molecules. We can't get it confused with the bond that happens between atoms. So it's not the same as the bond that happens right here. It's not the same as this bond. These bonds are covalent bonds. They are between atoms. The hydrogen bond is different. It's happening between two different molecules, between, in this picture, molecule 1 and molecule 2. Another really important thing to remember, this bond is weak, and that's going to be important. It's strong enough to make a difference in how water behaves, but it's not going to keep the water molecules as closely associated as atoms when they bond together covalently. And not only does it occur between water molecules, but it can occur between water and other polar molecules. And remember, polar means that it has a charge, like positive or negative, because then water can interact with it. It's like they speak the same language. So here's just another picture of hydrogen bonds. So in the first one, in this picture right here, you have hydrogen bonds happening between all these water molecules. So here's water molecule 1, 2, 3, 4, and 5. And let's just go through and highlight the hydrogen bonds. Boom, 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 boom. And remember, if it helps to draw this picture, you're going to want to draw it and label it. The hydrogens, all the little grays, because it's not labeled in everyone, all these little gray guys are positive. Positive, positive, all of them. And all the oxygens are negative. And if you are doing it correctly, you're always going to have a negative attracted to a positive. Never a negative to a negative, and never a positive to a positive. In this picture over here, the second picture, you have a hydrogen bond occurring because water remember, is a polar molecule, so this has a little plus sign. And nitrogen has a slight charge as well. And if hydrogen is attracted to it, that should tell you, I want you to take a minute and think. If hydrogen, the positive part, is attracted to it, then the charge on the nitrogen must be what? Take a minute. If you said negative, you are correct. So again, opposite charges attract to each other. So these two guys are sticking together by this bond right here because of this attraction between positive and negative. So how is hydrogen bonding helpful? Well, it gives rise to a whole bunch of properties. So the first property that it gives rise to, I'm going to put a little 1 next to this, is cohesion. So you've already seen this. This is when particles that are alike attract to each other. So this is when water sticks to water. So you can do this. Oops, let's undo that. So let's zoom in a little bit. So when water sticks to water, remember you have our oxygens bonded to your hydrogens. Oxygens are negative, hydrogens are positive. You don't ever just have one little water molecule by itself. So let's draw one other one. And remember, it has a negative charge. So the fact that this bond forms, which I just drew in yellow, that's water sticking to other water molecules. And that only happens because water can form hydrogen bonds. And one of the kind of cool things that this does is it creates what we call surface tension. And you have all seen this in action. So remember earlier in the year we went to the creek and a lot of you caught bugs that look like this, these water striders. So the water striders float on water. They don't actually break the surface of the water because the water molecules at the very top are sticking together so much that the bug isn't big enough to push them apart. So he can just happily float all day. You can also see this with a paper clip. You can get a paper clip to lay on top of the water really nicely because it's not heavy enough to break these little hydrogen bonds between the water molecules. So this surface tension is really the second property of water. So cohesion is the first property, which is just water molecules sticking together. And surface tension is the second property, which is due to cohesion and hydrogen bonds. So it creates this like really strong surface of bodies of water that if you are very light like this little bug, you're not going to be able to break through. And here's another picture. So imagine, guys, this right here is the surface of the water right here. All right, I'm going to erase that in just a second so that you can see. But that's the surface. And because water cannot stick to the air, so it's all like air up here. So all this is air. Water can't stick to that. So it's going to kind of really, really, really stick to the other molecules next to it. And it's pretty strong. So again, if you're a little bit like that bug, if you're very small like that bug, you can't break those bonds. It's just not going to happen. You, on the other hand, are too big. So we can float in water. Humans can float in water because we're less dense. But there's no way we are small enough to not break the surface tension. So we would break right through that and we go in. All right, so the third property is adhesion. So this is when water sticks to things that are not water. So different substances. So think adhesion like glue. We can stick two different things together. And there's a couple of pictures here. So in the first one, we have water sticking to a spider web. So water and spider web are not the same material. And it's forming these nice little beautiful droplets on it. And then there is this picture. So water is sticking to the glass in this little tube. So if we zoom in a little bit, what's actually happening here, and I'm going to pick a darker color. So here is the surface of the water. It's a little bit distorted because of the picture, but the water actually dips down like this. So it's kind of creeping up the side. This is adhesion, because the water, H2O, sticks to glass. And that should tell you, because water's sticking to it, that glass has a, if you said charge, you are correct. So glass is charged. It has a positive or a negative charge. I don't remember which, but it has to, because otherwise water wouldn't stick to it. So glass has a charge. So the fact that the water does this, it creeps to the sides, that is due to adhesion. And now we're going to kind of put some things together. So capillary action is number 4. So it's the 4th property of water. And this is when the powers of adhesion and cohesion combine. And it's exactly the picture that I showed you before, except in living things. So inside of plants, there are these little tubes called xylem, and they help transport water from the roots all the way to the leaves. So they're very, very thin little tubes. I'm going to pick blue for water. And it's a long journey, right? So it's a long journey to get up from, all the way to the roots. Maybe, some plants, some trees, it's going to be hundreds of feet in the air. So cohesion and adhesion work together. So adhesion means the water sticks to the sides of the plant. Sticks to sides of the plant, of the tube, of the xylem. And it's cohesion. I don't even know what that was. I don't know how to undo that. There we go. All right. And so I don't even know if that's going to show up for you guys. And then cohesion is because water pulls the water behind it up the tube. So the adhesion, again, is it sticking to the side. The cohesion is the fact that the water molecules kind of pull each other up as they're creeping up the sides of the plant. So really, really important for their survival. Also, something that water does is it helps us moderate the temperature of the earth and of our bodies. So you all have experienced this. So we moderate temperature. If you go down the shore in May, so Memorial Day, it might be really hot out, so it could be beautiful outside, but if you try to go in the water, it's really, really cold, even though it's really nice out. And then if you go again for Labor Day, which is in September at the very end of summer, it's probably really nice out as well, but if you try to go in the water is warm, it warmed up. Because what happens is it takes all summer, the entire summer, to add enough heat, to add enough energy, because that's really what heat is. Heat is a form of energy, to heat water up. So in this way, water, like the oceans, can absorb a lot of heat for the earth, and the earth might not change temperature as much. You know this too if you try to boil water for you're making something for dinner. It doesn't happen very quickly. It takes a lot of energy. You have to wait a little while to heat up that water. And the reason that this is because remember, those water molecules act like little magnets because of the hydrogen bonding. So again, can't draw enough pictures. So here's our one water molecule. A little positives on our hydrogens, negative on the oxygen. And then here's the second water molecule. And I'll draw a third one up here for good measure. So these bonds, these hydrogen bonds, hold the water molecules together, even very, very slightly. So what we need to do is we need to add enough energy to break these bonds first. Because when we add energy, what we're asking the molecules to do is to move faster and faster and faster. And to get the water molecules to move faster, we got to overcome those hydrogen bonds. We need them to not matter anymore. And this is helpful in your body. So you can go outside in the heats and you don't overheat. And it's because you're filled with water. So water is going to help you to regulate your temperature. So it's important for your life as well. Something that people don't think about is water in different states. So water is unique in the fact that in its liquid state, it's actually more dense than it is when it's solid. And what happens is, so this is liquid water right here, and the molecules are moving around. So they're constantly moving. But when we slow water down, so when you put water in the freezer, what you're doing is you're slowing the molecules down. You're asking them to stop moving. And because of these hydrogen bonds, because of the charges on the water molecule, they're very particular. They want to line up in a certain way so that all of the parts are happy. So we don't have two positives lining up with each other or two negatives lining up with each other. So what happens is, in here, this is ice. Look at how much more space is in between these molecules. Look at all this. So much space. Over here, right here, there's like little areas, right? So it's much less space because the molecules are constantly moving. So it doesn't matter as much. Why is this important? Well, because ice floats. And you don't live in the water all the time, so it's maybe not as important to you, but there are plenty of organisms that live in the water all the time. And it allows, when it's winter time, which is coming up to now, it allows life to exist under the ice. So if ice sank, entire bodies of lakes and rivers and ponds would freeze completely solid, and you would have little fish popsicles, and they would, nothing would survive the winter. So ice floating allows liquid water underneath of it to still exist, and it even insulates it, which means it helps keep that liquid water at a more stable temperature. So it allows life to persist even though it is winter. And then we are going to do a Bozeman water video. So that is something that you should go watch now. The link has been provided to you through my Canvas site. So make sure you go watch that. I hope you learned something, and I hope this was a good review.